Let's start with a problem that's going to lead us to a definition. Find all functions that have derivative y prime equals x plus sine of x. This has me thinking about the second corollary to the mean value theorem. The second corollary to the mean value theorem states that if I have two functions with the same derivative on an interval, then those functions differ by at most a constant. Well, the second corollary to the mean value theorem gives me my method of solution for this. If I can think up one function that has this as its derivative, then every other function that I'm looking for that has this as a derivative is that one plus some constant. So I can write them all down by writing the one I've thought up plus some constant c. So looking at this, I just need to find a function whose derivative is x, and then a function whose derivative is sine x, and add them together. Well, what I really liked about these problems the first time we met them was it was just about thinking up an answer and thinking about our rules for the derivative. So I need a function whose derivative is x. So I think to myself, well, if I had an x squared, its derivative would be 2x. And if I multiply that by 1/2, then I get what I'm looking for. The derivative of 1/2 x squared is x, and I really just thought my way through it. And now I need a function whose derivative is sine. And so I'm thinking maybe cosine. But if I take a derivative of cosine, I actually get a minus sign, so I need to change that sign to cancel it out. And now the second corollary to the mean value theorem says, hey, to find all of those functions with that as its derivative, just add a plus c. So now I've gone from a derivative to every possible function with that given derivative. Well, this is what we're going to call an antiderivative. And in section 4.8, we define antiderivative and start to learn about those rather than the derivative. Every process we've ever learned in mathematics, always if you went one way, you could go the other. So we've learned how to differentiate, and now we're going to learn how to antidifferentiate. But the second corollary to the mean value theorem is going to come into play on almost every one of these problems because of that plus c. That if I can find one function with that as its derivative, now by adding that plus c, I've found all of them. A function big f of x is an antiderivative of little f of x on an interval I if big f prime of x is equal to f of x for all x in I. Literally just defining an antiderivative to be a function that if I take its derivative, I get back where it started. So I have two problems here. And in problem number one, I'm asked to find an antiderivative for this function. Well, I'm looking for a function that when I differentiate it, I will get this equation. So I'm thinking of that as the little f of x from above. And I'll write my answer down as a big f of x, which is a pretty standard convention that if my function is little f, its antiderivative will be represented with a capital F, and if my function were a little g, I'd represent its antiderivative with a big G. So now I just need to think up a function that has this as its derivative. Really no different than the thinking I had before. So I'm thinking, well, the derivative of an x to the fourth would be an x cubed, but the derivative of x to the fourth itself would be 4x cubed. So if I multiply by 1/4, I fix the problem. And now I need a function whose derivative is 2e to the 2x. And if I just think about it, the derivative of e to the 2x is e to the 2x. And here I've satisfied these instructions. I was asked to find an antiderivative. And that's one of them, is an antiderivative. Now, what's fun about this problem is you could actually come through here and say plus 2. Because now that's still an antiderivative for that one. Or you could say plus pi. Because maybe pi is your favorite number, and still this function's derivative is the one that was given. All right, for contrast, the instructions change slightly. Instead of finding an antiderivative, I'm asked to find all antiderivatives. So over here, I would have to tell you that, well, it starts off exactly the same. But instead of not adding anything, or adding 1, or adding pi, I have to tell my reader that all of the antiderivatives follow this format. That's 1/4 x to the fourth plus e to the 2x plus some constant c. Problem number 1 over here is really a request to find one particular antiderivative, and then this one is instructions to find all of them. This is one thing, and this is infinitely many things. If you're asked to find infinitely many things, you have to remember that plus c. If we're asked to find all of the antiderivatives, then I really do need that plus c, because if I don't write it down, I found one out of infinitely many things. And that's not really that many things. Sometimes, instead of being asked to find all antiderivatives, this is written down as finding the most general antiderivative. So if you see the instructions to find the most general antiderivative, that's also asking you to find all of the antiderivatives. One more example. Find the most general antiderivative for g of x equals 2x squared. All right, so nothing too interesting here. I'm asked to find that most general antiderivative. So I'm looking for all possible functions, big G of x, that have this as its derivative. Well, I'm thinking that that should be x to the third, but if I multiply that by 3, I get 3x squared instead of 2x squared. So I'm thinking this needs to be a 2/3 x cubed plus some arbitrary constant c. Okay, so I understand what's going on there. G of x is always a cubic function plus some value c. And I could actually understand that as a crude sketch, right? 2/3 x cubed's graph would look something like this. But if I added a positive number to it, it would simply shift that graph up. And for different constants, I would shift it up different amounts. Ooh, don't know why that one curved, funny. Just a cubic function. These should all have exactly the same shape, but shifted up. And if c were a negative value, then my graph would shift downwards. And so what I have here is a picture of some possibilities for 2/3 x cubed plus c. Well, let's ask one more question and see if we can find an answer. Find the antiderivative that passes through the point 3, 4. All right, well, I have all of these different antiderivatives and more that I didn't even draw, and then now I'm asked to find one of them that passes through the point 3, 4. So I can imagine maybe the point 3, 4 is right there, and that would tell me that I was looking for this particular function. So it would actually be for a specific value of c, not just an arbitrary one. So let's see if we can find that value of c. I have an x and a y. So if I plug in x for x and y for y, I should get a true statement. So when x is 3, g of x is supposed to be 4. And then 2/3, 3 to the third plus c. I can use this information to find c. 3 to the third is 27. Divided by 3 is 9. 2 and 9 multiply together to give me 18. C is equal to minus 14 when I solve that, and that lets me write down this specific antiderivative that behaves in the way I was asked for. What I realize now is that my picture is horribly not to scale, and apparently something more like this goes through the point 3, 4, which must be something out there, because my graph actually shifted down to find it.